But by the time we reached here, it was already late, right? And that resulted into a system being isolated into the four asynchronous island. A lot of people lost power. The truth is that we could have, if we detected at this stage and took some control action, which is very simple, just isolate the load. All of these state could have been avoided to not have a power, right? So this thing could have been avoided. And how much was needed? Later, of course, it was not done at that time. Later, we found that only 0.4% of the total load, if we could have detected and we could have operated my spatial protection system, which is automated control, we could have saved the blackout, right? And in fact, how much you need to drop? Only 0.4% and only for 30 minutes. Of course, it was easy to figure out this number by re-simulating that what happened. And if there was automated control to figure out that where to shed load, because it's not about shedding load anywhere. You have to shed the right amount at the right location to avoid all these events which is happening here, right? Like a generator is tripping because of high megawatt. If you detect it and set the load, it will not happen. Okay, so it is a trade-off that if you take the action too early, you're isolating the load which should not have been, and you're losing the money on that. But if you delay it too much, then things will become out of control. And once it's out of control, these action will not help. You have to shed more load, but it's still possible to control it, just like this one operated. But this is already late, and then the blackout happens. So how to find that balance that it's not too early, but it's not too late either. That you don't. Basically, we want to be in this area. We don't want to go in here, and definitely we don't want to go here. Another report that came out in August, 2003 blackout, it also indicated that we could have dropped 1500 to 2500 megawatt, which is very low percentage of all the power that we lost. And that has been leading to avoiding the loss of another line which happened, which led to a more number of line outage and could have been prevented the blackout. So there are different industry and operator which are also thinking about that and putting some automated control, but sometimes it's enough, sometimes it's not. So for example, Hydro-Quebec in Canada is looking at the long distance between generation and load. There are geographical constraint, and if you have a long distance, basically there are more losses and there are more drop, and they want to make sure that if extreme contingency happen, how do you make the system still performing okay? So what they will do is that they will drop the generation, they will drop the load, and also they have load shedding and under frequency load shedding. So under voltage load shedding and under frequency load shedding. If you look at EDF, which is in France, they also have the similar things, but for their purpose is different. Here it is long distance between generation and load. Long lines relate to different kind of impact on the system compared to highly meshed and interconnected. It's because it's more populated and high density, right? Well, Canada, most of the population is not dense. So what they want, of course, avoid all collapses, voltage and frequency collapse. They don't want it. Cascading definitely don't want it because that lead to blackout and loss of synchronism. Then they have a SPS in place, which will look at the generation start, load shedding, even the tap changing transformers set point modification, shed the generator, which is called generation rejection, and then under frequency load shedding. Now, if I think about, can I apply machine learning and AI, right? When we do that, we have to be very careful that we don't forget the physics. And that was a purpose yesterday that when you learn about physics aware machine learning, which is very, very important. And if you see here, it starts from here. State estimation, that's physics based. But what happened that when your system is stressed, your mathematical equations, which is giving you the system status, is based on certain assumption and approximation. Most possible assumption is that it is a second order or first order system, and that's how we can solve it. If you go for third order, fourth order, you cannot solve it in a given time using the same set of solution technique we have. So which means that with that approximation, we can do something, but when the system become extreme, my state estimation may not converge, may not give me the solution. And if that happens, we need to develop some kind of reasoning and algorithm which will help us to make a still decision. And rule-based is one possibility. There are a lot of smart people who can develop a rule just based on observation that what action to take, which is not 100% solution, but it is moving towards solution by 60 to 70%. We also want our machine learning to, which is really good in forecasting and learning. And these kind of tasks, we want, some kind of machine learning. And then the trend is now is to go to agentic AI, which is kind of better because you don't rely on the single AI big machine, but each agent is running at substation or running at even within the substation is looking at some part. And this brings, ability to adopt, ability to do like a teamwork, coordinate and negotiate, which is not possible with a single machine doing everything. And that brings the multi-agent system, right? But here multi-agent is not regular agent, but it can optimize, which is which is a very tough task if you think about distributed optimization. And it can adopt, because if one agent fails, it's okay, rest of the agent will solve the problem. So different architecture is possible. Which one is better? It really depends on the problem. But at least I think that some kind of Holonomic architecture, which is a combination of all of these, and targeted towards a specific solution in each of those layers, or local, which is simple solution, but with very less, because there's no communication in local typically, will be more secure. So combination of these, which goes into Holonomic, will be much better, where intelligence is embedded into each distributed agent. Why? Because our system is being distributed with the DERs and more local generation. Things are different, right? So that's the centralized is not going to work anymore with similar kind of reliability that the way you used to have that in the past. So talking about more like a strategic power infrastructure defense, we are basically talking about if we go towards this decentralized and distributed path, then we'll have a more adaptive configuration schemes, self-healing strategy, and to achieve this, autonomous, adaptive, and preventive action, or remedial or corrective action, or even preventive is possible if we design it in that way. So it will provide better protection, which is more coordinated and intelligent, and minimize impact on the system vulnerability, and then definitely increase the resiliency. Well, it's very easy to say here, how do I design? How do you design this in autonomous way which can adopt? It's a big thing. It can take years and years to design such a system. And that's why we have to break this problem and say, let's focus on only solving the voltage first. Then let's focus on only solving the frequency, right? And then once all of these done, then you combine that together with a big team effort to make it happen. Control islanding, which already has been used in the past, by different utilities, is another solution. What you do is that you look at the system, and you know that you cannot keep the integrity of the system in a connected mode because it will collapse, and blackout will happen. So you look at that how I isolate the system into two part or three part or four part, and keeping the power balance in each group. There are multiple advantages because if there are chances of why do we keep the system operated in integrated manner? Because it helps to share the resources and helps with the economics. So the power goes cheaper if you have a bigger system operating together, right? But in extreme scenarios, the disturbance also will propagate in the system at the same speed if it's all connected together. And if there is a chance that it will collapse, then you divide the system into smaller. So if even if it collapse happen, it will only happen in one island. And when you say island, we are still talking about a pretty big island, which is maybe bigger than state or within the state. So by doing that, we basically stop the propagation of disturbance and contain it into a single island. So we have to do the islanding scheme as soon as that we detect that something is happening, and it might propagate to the whole system. Disadvantage that comes with that, the current island has only local point of view, which is sometime needed, and separation points, we cannot make it adaptive, right? Because unless there is a switch and there is a balance of generation and load in each island, you don't have, so this already constrained so much that we cannot make an island the way we want it, because you have to find a switch and you have to find a balance in generation and load at that given time. So this configuration, which we are taking the grid from, mode 1 to mode 2 or mode 3, is will be very important. That how do we defend against extreme events? We don't want that to propagate. And a single change in configuration, which is typically done for the power outage, in transmission, it is done typically, if you look at the system theory, there's something called weakest link. And weakest link is saying that you have a transmission network, which is, and weakest link is typically more applicable for the mesh network compared to a radial network. And sometime by taking the weakest link out, you actually make the rest of the system much more stronger, even though you're operating with less number of component. So that's how the configuration helps. Here, it must be that how do we do that configuration should be, more intelligent looking. And when we say intelligent, we are not always talking about AI. You can make actually intelligent things with applying your math and physics in such a way that it can look ahead, right? And if it can look ahead and predict things, it is already intelligent than if it is not able to look ahead and predict things. So by islanding, what we want to do is that if extreme event happen, cascading happen, it will be forcefully making multiple island with several outages happening, and then system will collapse. We want control islanding. So instead of cascading and protection operation making islands, which is an uncontrolled way, we want to take some grid configuration strategy in advance. So we create island in a way which is balanced, which means that each of these has a power and balanced, and also voltage and current can be controlled, and system survives. And that's what we want. So other power system mitigation strategy that we can do is, we talked about multi-agent, which is distributed, and that will help in doing the autonomous way, some preventive and corrective self-healing control strategy, adoption of the protection system with the context of wide area measurement and control, and also some mitigation strategy, which is monitoring the real-time data for voltage stability, tangent stability, oscillation, frequency instability, and voltage control. And then you have to keep a balance between proactive control, because you don't want to take a control and isolate the generation and load, which will be a problem for the system. But you want to check and validate very carefully that it is really stopping the further cascading or further propagation of the outages. And then sometimes you have to do the reactive control, you have to do adaptive versus optimal control. So there's a lot of research that need to be done. That how do we do this kind of things, right? And that's why it's still a research topic. Now talking about IT mitigation strategies. So we talked about intrusion detection system, which is basically the whole job is to detect anomaly in cyber data. So we're now talking only cyber data and cyber measurement, and then try to find classification, and then send the control command to block the intruder. And like I said, that it can also be done with the software-defined networking, which is very new. So in terms of tools, that how do I detect that something is wrong, right? There are a lot of tools. In fact, I would say like at least 50 different tools that exist, if not 100. There's some which is free, and Nmap is one of the tool, which is, I think it's become commercial now, but it used to be free. What it does is that network map. So if I don't know the network, that how the data is flowing, I cannot do much that where the attack originated from. So network modeling based on the actual data flow is very important. And ZenMap, or which is using Nmap, can do that. Wireshark, some of you probably have used. It can be used to monitor and track the packets. So all the digital data packet which is flowing, we can actually detect that where it's originating from and where it's going. And it is all in real time. There's other tool, like one is called Metasploit, which is for vulnerability exploit tool. It can be used to, basically do the vulnerability analysis and define the security issues and security assessment. That if you implement some security solution, vulnerability still exists or is gone. Because vulnerability, if it exists, but access control is not there, then of course no one can exploit that vulnerability, right? So vulnerability is the first step, that where the attacker is able to get into the system with access control. Here's another one, OpenVAS, which is a framework for several services and tool, which offers vulnerability scanning and vulnerability management solution. There's also, we talked about IDS. So this is Bro and Snort is one of the popular intrusion system. And remember that we did not talk about a lot of those commercial tools, right? Even though now some of these are also commercial, but there are so many other tools out there which is commercial, DRSec to Dragos tool, Neighborhood Watch, which is also from Dragos. Those all can do it too, with the different focus. So Snort is lightweight network intrusion system, and then Bro is also, which is more comprehensive. What it's doing is finding the anomaly in the set of data that it is trying to capture with data packet and networking information. And then there is a lot other things possible, right? So once you detect something using Bro or Snort or any other tool, then network segmentation is possible way to isolate the critical OT system from external network, right? So this is a very important defense mechanism that we typically use. And remember that we have emphasized this point a couple of times, that you can have vulnerabilities, but unless someone can get into that device, it will not be compromised. So vulnerability and access is the first two things which will be used by attacker to compromise the system. And if you use the good access control, whether role-based access control or multi-factor authentication, which even banking has implemented already. Like, so if you have if you're trying to log into the web of banks services, typically you'll get the OTP in your phone to get the multi-factor authentication, right? So same thing, you can implement it here. The problem, it slows down the process. It is not very convenient, but definitely it makes it more secure. So privilege-based principle to minimize the risk of unauthorized access is really important. Just this topic, there are hundreds of researchers and so many tools out there that how to do this access control. Because this will change, most of the attack that is happening, it will stop it. Patch management. So if you find the vulnerability, of course you need to patch it. You need to fix it so that it's not vulnerability anymore, right? So updating, just like you update your software, either it's Windows or Mac or Linux, we also need to keep updating the software inside the digital device. So we maintain the OT system, software, firmware, hardware, to address any known vulnerabilities. This is not going to help for unknown vulnerabilities, and that's why a system still gets hacked. Even patching thousands and millions of devices, if you talk about IoT, is not easy because we cannot take out those systems out for doing this, because there's this operational device and should work 24/7. Anomaly management, we talked a lot about this in IDS, how to detect, how to classify, and find the root cause, which is important. Monitoring and incident response. So once you detect anomaly, how do I respond to that incident response, right? And sometimes you don't want to take action too soon, right? So like this is, of course, one action you can take, network segmentation, but this has to be done in the advance. And here we are trying to do the same thing, but in operation, so that we can isolate the attacker and that small area. And we have to look at the more data before we take the response, before we do something. Logging is important, incident response is important, and then also rapid and effective responses to contain the attacker or eradicate the attacker, and sometime recovery procedure with that, how, if once it's isolated, how do I recover services which has been already out because of this isolation. Just like production operates and the power grid will be broken at some point, which will result into a power outage. So here also, once you take the segmentation or isolation, some of the IT and OT services will be stopped, and you have to restore it. Now, this is very important that when we try to do these things, and if you remember that we talked about that human interface is actually 95% of the cause of the attack, because some human which clicks things wrongly on email link or some other ways is the first access point for the attacker. So how do we train? How do we continuously improve? By training and education, and continuous improvement by evaluating and updating cybersecurity measures, responses will be very important. So looking at this, we talked about access control. And access control, the first thing is authentication. That how do I know that this person who is trying to access some machine is authenticated and authorized to do that. So this process is very important, and approaches that we can apply is, of course, there are challenges in doing that, and so human limitations to ability to identify that what's good, what is bad, is a problem, and digital compromised, which is scam and phishing that happens. So what's something a person knows, that's what we are trying, that's what attacker is trying to find out. Their security question they're trying to find out, they're trying to find their password, they're trying to find their PIN number, right? Something a person possesses is, it could be this RSA kind of a security key, it could be smart card, it could be fingerprint, it could be cryptographic key, phone, where attacker is trying to steal it and it lies if they forget about it. The user has forgot. It is typically expensive to distribute, but it's possible. What something person has is fingerprint, iris information, which is eye, and then hand, and then voice, right? So all of this can be used for, and which is typically, the problem is that it might not be private, because someone can even take the pictures on the social media and try to find their iris. Might not be same if it's a 3D iris scan, but then you can get the video and try to steal the identity with that. So it is error prone, but one option that typically works is multi-factor. So if even one thing is gone, we make it second thing and then third thing. So in that way, you authenticate in a double check, not triple check. Access control, again, very important, which is it determines that which subject, user, or processes can access the system files, resources, or execute instruction. And we do that in a way that object owner determine who has access, right? So it's like a privilege based access, mandatory based access, where a security administrator determine that who has access to the objects. One team is deciding, security administrator, not the object. Role based, where the subject's role determines their access to the file. So vendor will have a different set of access, and again, these are something that is already implemented. Like if you're doing the online thing, the instructor will have a higher access than students, and an administrator will have even higher access than instructor. Same thing for the vendor, engineers, operator, they will have a different kind of access. Attribute based, where we are trying to do the user attributes, define that class 1, class 2, class 3, and then we'll give them privilege based on that. How do we enforce it? We can enforce by hardware processor, by putting that logic, or by doing the software, which is operating system and servers, following these set of rules. Firewall is very important, very highly used these days, where we put the firewall in between, and this is public internet, and this is the network for IT and OT, and we make these rules that what can flow in and what cannot, and filter information in such a way that you can sometimes get the information in and out, but this set of data cannot get in, right? So we stop this data. And same thing, that data leaving the network is stopped right here. It cannot go out, right? Because those are sensitive data. Other technique we use is whitelisting, where we basically tell that what IP should have access and what IP should not, right? And if we know that this machine is only going to be accessed by 3 different machines, then we only allow that. It is very restrictive. This is the inconvenient, because every time vendor comes, you need to whitelist and then block it again. So the more management is needed to allow for maintenance and other things. So whitelisting is basically selected IP MAC has access, everyone else is blocked. Other thing is blacklisting. Blacklisting is that everyone has access, but this set of IP and MAC is not allowed to access it, right? Whitelisting is much more restrictive. Blacklisting is less restrictive and less maintenance required. But of course, whitelisting is more secure and blacklisting is less. Now, if someone does the IP spoofing and they know that what is whitelisted, they can get in, right? But it's not going to be easy to find out that what has been whitelisted. And then we have software-defined networking, which we talked about, where by software or by programming it, we can, not on the fly, but we can define a multiple layer of the routing process, right? So how the network packet will be forwarded and routed in the control plane can be defined in the software, and when it's needed, that's how it will do its thing. So it's a flexible way of managing the data packet flow. And the control plane, which is the routing process, can have one or more controller, which is kind of a brain of software-defined networking. So same thing can be used for making the system, recover faster. Security protocol, which is also very important because that drives the data analytics. And we used to have the internet, which was insecure in the past, with HTTP and DNS, and transport being TCP and UDP, internet protocol, IP, and network. Over the time, we learned that how to make it secure. So now, if you're browsing and you're still opening the HTTP, you should not, because that's not secure. But anything with HTTPS is more secure. And so that DNS is not very secure, but DNSSEC is secure. Transport layer, so these are different layers, right? TLS is more secure, datagram TLS is more secure, and so that IPsec is secure, and network is more advanced one is more secure also. Different cryptography mechanism, and then we use like symmetric key, asymmetric key, which is different kind. Will of course make the data secure because it cannot be decrypted by everyone, but only who has a key. And authentication, we talked about that, and hash function, which is one way of doing that. Last thing which I want to talk about is NUG-SIP, which is basically about federal rules which is applied and required by each utility group, that how to make the system more secure. Is a critical infrastructure protection SIP standard, and it is right now it's typically applied to a transmission network or bulk power system. It is proposed by NERC and signed by FERC in our case. That allows NERC to charge if someone is not following these rules. And there are a lot of versions. This is the actually older version, V3 to V8. But I deliberately selected an older version so that I'm not giving you most recent information. So version 3, what it will tell you? It will tell you that how to manage your security protocols, how to keep the electronic security perimeter, right? How to do the system security management. So there's a lot of detail, but basically you can think about this is a set of rules that every grid operator need to follow, especially for the bulk power system, an important one, which is also coming from NUG-SIP, that what is important and what is not, and what is the priority for that. So how to use the password and how to, small things which is important for the security. Going back to SDN, like we also did some research, and we demonstrated that even though SDN is designed for to make the communication of data packet more reliable, you can actually use it for some kind of security. So we set it up in our lab with multiple IEDs and software-defined networking, and then the process bus, and then what we did is that it all talks to the within the RTDS with the power grid. And we also have these kind of DNP3 GUs, SV OpenFlow kind of protocol. And we want to use that as a two different options. So network option A is SDN, network option B is traditional, and we want to see that is there any improvement in terms of different attack. And we found that there is different improvement that is possible once you configure your SDN and networking. And the action that you get is that you'll see the result very soon, that for different kind of event that happens, SDN controller, which is here with the station bus and process bus, and again, this is only one way of configuration that we do with the SDN. It is because I can program it in such a way that it can go from merging unit to IEDs to SCADA in this way, and it will allow some packet and will not allow some packet. While traditional network is typically based on multicast, which means that if it sends the information, it is also sending to the here and here too, right? So it is multicast, which means that anyone can receive that message. Of course, if you don't set in that way, it will not happen, but this is a common practice. While here, I'm controlling that where the data packet will go. So either it's SV packet multicast or Goose packet multicast or ERP packet broadcast. We are controlling that where to deliver. And then with all these setup in the same way that we just talked about here, merging unit to IDs and then to the SCADA, which is one of the device that we configure in our lab. You can see that there's a big difference with network failover and multi-protocol cyber attack, and how the traditional response, how the hybrid will respond, and how the another configuration will respond. And if it's a full SDN, the resiliency score comes out to be very high. And resiliency score is the same one that we talked about earlier with a certain definition, which is factor based. So SDN gives a much higher resiliency compared to other traditional device. We also did the second thing that we developed a lot of different tools, which you already have learned in some way. So this is the system with the cyber and physical system. This is a kind of Fixisys Cascadia, which is Washington State system. And then we have a PMUs and ID connected with RTDS, and we have a substation devices. And then finally, we have a control center, with PingThing, working with PingThing, which is a company we already talked about, Super PDC and SCADA. So this is the system we got. And then we used some of machine learning and physics-based to develop this Sync ADC, which can detect, which can classify, and localize based on the PMU data. And we also use CP-TRAM to do the resiliency score, which is the same thing that we talked about in the past, resiliency metric. And this work as our trigger that something is going on, some anomaly is there. We also have this, power simulator, which is like a EMS you can think about, working with, we work with the Inksys and Power Data Company in Seattle. And all this system information, so this is the system, cyber physical system, this is a monitoring layer and control layer. And then we are getting it to converting it to cyber power alarm tool, which can give the data to the power grid operator center, because they don't need much information about cyber, right? Because they're not trained for that. So they are power grid operator. They should not get much information about cyber. Only thing that they should get is alarm that's saying that don't do it, do it. And that's how we configure. So they don't need to know about these things, but only single alarm, do it or don't do it. And then we have this operator, being monitored with the stress and eyeglass sensor, so that we can see where they're looking at. And then we did a lot of different attack, which I can map to the MITRE framework. And we took again a couple of different kind of attack vector, which you can map it. We do the step 1, step 2, step 3, with the final goal being the impair the process control. So here we open the breaker, which is very similar to Ukraine attack, if you think about, and we put operator under this kind of attack, following these steps. They don't need to know about these things, that how it's happening. They only need to know about the final alarm that is coming, and then make a decision. And you see that we had the transmission operator, we had a distribution operator, we had a power student, we had a non-power student, and the time taken to respond to that will vary, right? And the accuracy will also be varying, which we captured. And you can see that the transmission operator were basically able to take the action pretty well, while the other were not able to. Some transmission operator, of course, a little bit confused because they are trained already without these kind of alarms. But most of the time they will, like their time taking and learning was much smaller. So if you take the average of this, they were the fastest, right? If you take the average of this, it will come out somewhere here, while this average will come out somewhere here. So let me stop here and see if you have any question. We just demonstrated some way to basically defend and make your system more resilient, right? But a lot to do using this cyber physical system. So let me go back to the questions. As you focus more on AI based on detection, what is the relevance of rule-based detection using logic controller? So one thing is that we should only apply ML and AI only when our simple approach cannot solve. Why simple? Because simple is more robust, less error prone. We don't even know that once we put the AI, what kind of vulnerability will exist in AI tool, because AI is also software, and software, all software has some kind of vulnerabilities. AI vulnerability has not been determined yet. So if you can make it simple, it will be better. So rule-based detection will be still better if it works, certain threshold like 80%, 90%. It has a limitation. Rule-based always has a limitation because it cannot solve the complex detection problem. But if you're looking at the one device and there are only 5 variables and it has to follow certain protocol, there's no need of AI and ML. We have to apply the rule-based. If you're looking at the multiple devices with a lot of different variables, and rule-based is going to kind of explode because of a problem of a complexity of the system, then we have to go for the physics-aware AI. Now, physics-aware AI you cannot apply to the cyber system, because cyber is not following the physics, right? Cyber is following the network rules. Cyber is following the data packet protocol. So when you say that for cyber, we're talking about protocol aware, we're talking about networking aware, we're talking about system information aware. When we're talking about the power grid, we're talking about physics aware AI, right? Or system aware AI. So it just depends on that what kind of things we're trying to do. But I think we should not give up the simple approach if it works. So it can be combined and integrated together for real-time detection, because rule will be the fastest actually, right? While AI can easily complement the rule-based approach in future. So I totally agree with that. To make fully autonomous control, it will take many years, as sometime manual operator intervention may be required. It is still possible to automate the operation, let's say network microgrid. Yeah, so it still is possible. Again, we have to make sure that as much security principle we can apply is there in automation, so that it is not compromised, because the same automation will be used by attacker also. And then difference between autonomous and adaptive control. So something can be autonomous, like a protection is autonomous, but it is fixed, it is pre-planned. So you tell the relay that, okay, operate autonomously, which means that you detect something, open. You can, and then you tell that you don't open too fast, right? So wait for 3 to 4 cycle. Sometimes 16 cycle is typically done, so that you don't open on fault, which will automatically go away in few cycle. So it's autonomous, but it's not adaptive. It's not adaptive because we are prefixing the rules for that controller. Same thing for RAS and same thing for SPS. If you're deciding in advance that if this happens, do this. If this happens, do this. And you cannot make this rule too many. And then if something happens in between, then it does not know what to do, and it will take action, but it might be wrong. While adaptive is more fine-tuned in a real time. So we tell some rules, we can tell some rules, but if the operating point is between those two thresholds, then it will calculate something in on the fly and then take a control action. That will be adaptive, which means that it is adapting with the changing power system operation condition. While autonomous can be adaptive or can be pre-designed control. Right, so that's the main difference. For network segmentation, can SDN switch be useful? Yes, it can be. Of course, SDN is also pre-planned, pre-designed, but we can tell that with SDN and adding more devices into that, which can help in network segmentation, because SDN is for routing the data packet, right? Not to switch in and switch out, but we can combine some logic to make the SDN work for network segmentation also. But after network segmentation, SDN will always work, because now it is trying to find a new path, and which is predetermined to further data packet. So SDN will be definitely helpful after the network segmentation, but we can combine these two together to make work better. Will the IEEE C37.18 protocol dissectors help in decoding synchrophase data in Wireshark? So Wireshark, as far as I know, it will only find that where it is originating, where it is being delivered, and what is in the data packet. But yes, like you said, that if you use the additional, kind of dissectors, which is a different tool, then yes, you can. If it is not secure, which is actually it should be secure, and there should be some cryptography on those data packet. If it is not, then you can decode the data, and it is possible to basically get the meaning of each data packet bits. And how do you install them separately? So you can install them, but like I said, that you have to play with the synchrophase data to make it insecure, because unless you can decode, you cannot dissect it. So you have to basically turn off that security of coding and decoding if you use that, and you have to do that in two steps. So first, capture the data with Wireshark, and then apply the dissectors and decode, and pre-process that so it's already decoded. Okay, well, I'll stop here, and I will probably join for a short time tomorrow, but this will be the last lecture. And then I know that Dr. Gupta is going to talk next. Maybe we can take a few minutes break, and then she can talk.
Yeah, yeah. Thank you, Professor, for educating us the most need of the our cyber defense mechanisms and awareness on the cyber, how to protect the cyber, and your inputs and suggestions and details on every aspect. It's truly amazing for us, and we look forward to take your suggestions while solving the evolving challenges in power industry. Thank you, sir, for your course and suggestion, and your course is truly amazing, and we look forward to take your suggestions. Thank you, sir, once again.
Thank you.
Hey, Dr. Sonam Gupta, how are you? Uh,
Hi, good evening. Hello.